Good evening, everyone. So, today we'll start with the first chapter of your MSc classes. That is, the first block is inorganic chemistry, and we'll gradually, during the course of time, we will cover the different blocks that are present in here in this unit. So, today we'll have a look at block one. So, here in this block one, we will talk about different main group elements, the transition elements, and the structure of molecules. There will be also an introduction to organometallic chemistry. And this block here, in block one, we will come across three units. So, here in three units, the first unit is about the general characteristics of main group elements and the transition elements. So here in this unit, we will just have the basic properties of the various physical and chemical properties of the main group elements and the transition elements. The second unit, it deals with the structure of the molecules. And in third unit, we will be studying phosphorus nitrogen and sulfur nitrogen compounds. So before going into unit 1 and unit 3 and the other complex chapters, so we'll start with unit 1, that is about the general characteristics of main group elements and the transition elements. So here we will just have a revision of what we already know about the normal characteristics of general group elements. So here to begin with, we will talk about, we'll start with the general characteristics. So now first we will understand the electronic configuration of main group elements and the transition elements. So we know that the main group elements that we mostly talk is the group 1 elements and the group 2 elements. So we'll first discuss about their electronic configuration. So here in this table 1.1, you can see the properties or the electronic configuration of group 1 metals. So now we know that group 1 metals, they are lithium, sodium, potassium, rubidium, cesium and francium. So francium we won't discuss, we will consider up to lithium, sodium, potassium, rubidium and cesium. So when we look into their electronic configuration, they are called as group 1 elements because in their last cell, they contains one unpaired electrons in the s orbital. So here you can see when we see lithium, it is 2s1. For sodium, it is 3s1. Potassium, it is 4s1. And the rubidium, it is 5s1. And cesium is 6s1. Now, since the last electron, it goes into the s orbital, they are also called as s block elements and they are called as group 1 elements because here only one unpaired electron is present here in the last orbital. So the other general properties of these group 1 elements, like if we look into the atomic weight, so we see that as we move down the group, so that is as we move from lithium to cesium, the atomic weight, it increases. So here for lithium it is approximately 7, whereas when we look into for cesium, so the atomic weight, it becomes 132. So the general trend is that the atomic weight, it increases as we move down the group. So then there are other properties, like we have the covalent radius and the ionic radius. So when we look into the covalent radius, here we see the covalent radius, it increases from lithium to cesium, whereas for ionic radius, it also increases from lithium to cesium. Then the boiling point and the melting point, here we see it decreases when the boiling point, as we go down the group, then the boiling point and melting point decreases, but the density, it increases when we go down the group. So these are some of the common properties of the group 1 elements that we know. No, so here the in the second table we see the some of the electronic configuration and the some of the properties of group 2 elements. So now group 2 elements, they are the alkaline earth metals, whereas group 1 elements, they are called as alkali metals. So here in group 2, the mostly the elements, they consist of beryllium, magnesium, calcium, strontium, barium, and radium. These are called as group 2 elements. So here, when we look into the group 2 elements, here the last electron, here you can see it enters the s orbital, and that is why they are called as group 2 elements. The atomic weight similarly, it increases when we move down the group. So that is why that is similar to that of the group 1 elements. So here the ionic radius and the covalent radius, it also increases. The boiling point and melting point, it decreases. Here the boiling point particularly, sorry, here in group 2 the boiling point decreases because it is a full filled orbital, and you can see here it, the last one here we see it does not follow the trend. Then the density, here we can see the density increases, and the electronegativity and ionization energy, that we will discuss in details in the later part. So now this is about group 1 and group 2, that is the main group elements, and these are the general properties. And now we will talk about the transition elements. So what are those transition elements? The transition elements are those elements that lie between the S group elements and the P group elements. Since they lie between this S block and P block, they are called as transition elements. This is because the only reason they are called as transition element is that because they have their properties, that the properties lie between those of the S group and that is the P group. So here, as you can see here in this periodic table, that it has been shown, the here on the left hand side we can see the S block element here, and here in the right hand side we can see the P block element. So the elements that lie within this range, they are called as the transition elements. Now here the transition elements, we know it further, they contain the inner transition elements, or that we call it as the lanthanides or the actinides. So these transition elements, they are also called as d block elements because the here the last electron, it goes into the d orbital. That is why they are called as the d block elements. Now when we look into according to the definition of IUPAC, that is the International Union for Pure and Applied Chemistry, so certain elements are there which should not have been present in the D group. Like for example, zinc and cadmium, although they are present in the D block, but they are not transition elements because in these two elements the D block is completely here, it is fulfilled. They do not fulfilled or half filled. So here they, in these two elements, since it is fulfilled, that is why they should not have been placed in D groups, but it has been found that they follow some other properties of the D block elements, and that is why they have been placed in D group. So then here the transition elements, they have been divided into 4 series. So the first series of transition elements, that what we call it as the first series, that consists of scandium to zinc, the from scandium 21 to zinc 30, here 3d orbitals, they are filled. So here if we look into table 1.3, so we can see the elements from scandium to manganese, that is from atomic number 21 to 25, and here in this side, here you can see iron to zinc. So from 21 to 30, they constitute the first series of the transition metals, and or they are called as first transition series elements. Then the second transition series elements, they constitute yttrium, that is 39, atomic number 39, to cadmium, that is 48. Since the electron here, it goes into the 4d orbitals, they are sometimes called as 4d series or the second transition series or the second series of transition elements. Here you can see yttrium to cadmium. Then the third series of transition elements, that is lanthanum 57 and then hafnium 72 to mercury 80. They are all 5d orbitals. So what happens here is the last electron, it goes into the 5d orbital. So here this is how the lanthanum to hafnium and then followed by mercury. And then the fourth series, that is actinum 289 to here Rutherfordium, that is 104, to here it finally it goes to copernicium, that is 112. Here the electron it goes into the 60 orbitals, but here we can see they are called as the fourth transition series. But here we have come across in the third transition series and fourth transition series two very important observations we know we have, that is from here in lanthanum and in the fourth transition series actinum. If we look into the periodic table, then they constitute the inner transition series, that is the called as the first inner transition is called as the lanthanides, and the second inner transition row it is called as the actinides. So that is altogether a different part which will be studying later. So now this is the in general representation of main group elements and transition elements. So this we all know how the classification it has been made. So now we will talk about the penetration of inner electron which influences the distribution curve of various orbitals. Now we know orbitals they have been mostly of four types, the s, p, t and f. So when we talk about the penetration of electron, so here it follows the order that s is greater than p, it is greater than d and it is greater than f. So which means that s is more, it is the closest to the nucleus, followed by p, then d and then f. So here according to this penetration the different the arrangement of electrons they are made, and that we know they follow the Aufbau principle or the Hund's rule. So this is the general representation or the extent of penetration of the orbitals. So and we know how to represent different types of elements based on their orbitals and the number of electrons. So here we will now look into the radial distribution of 3d and 4s orbitals in hydrogen atom. So here in this figure 1.2 we will first talk about the of a hydrogen atom. Here 3s, 3p and 3d of a hydrogen atom they have the same energy, but when we take a complex atom then this becomes very difficult to visualize, because for hydrogen is the simplest atom, so the radial distribution function is easy to calculate. But when we have other complex atoms, then the number of electrons increases and the radial distribution function it also becomes more complicated. Like supposing where for complex atoms we have ns orbitals, so now for hydrogen it is 1s1, so it is easier to comprehend. But suppose for other atoms which has ns orbital, then it will be followed by np orbital or the nd orbital. Like suppose we consider the 4s orbital here, so 4s orbital it will lie in the energy is low than that of 3d, that we know. But when we see the 3d orbitals get filled up with some electrons, then there are some other changes. So here if we look into this plot, so here this is for a particular, here the red plot it indicates the radial distribution function for a 3d orbital. But when we have 4s atomic orbitals in H atom, then the radial distribution curve it changes. So here after addition of other three electrons into the 3d orbitals, then what happens is because of this addition of the electrons, the energy of the 3d orbitals it falls below the 4s level and the energy changes, because of which the effective nuclear charge it also changes, and hence the radial distribution function it's also changes. So this is how the distribution radial distribution function is affected by the number of the electrons that is added or taken out from the shell. So this is how we talk about the radial distribution function. Now here, if we look into the configuration of copper. So copper we know it comes from the it's 29 and it comes from the first transition series. So before copper, nickel is present. So if so for copper, this is the electronic configuration of nickel is argon 3d8 4s2. So for copper, it should have been 3d9 4s2, but the actual representation of copper is we know that it is 3d10 4s1. Now why this representation. Why it is preferred? Because here we know that the d orbital, the completely filled d orbital, it is more stable. Either half filled or completely filled d orbital is more stable, and that is why. So here what we see, instead of 3d9 4s2, copper comes as 3d10 4s1. So this is how the exchange energy, pairing energy, and other radial distribution function works out. So now we will talk about the different periodic trends in properties. So first is, here we will see sorry. So first, here we will talk about the various periodic properties. So first we will talk about the ionic radius, different types of radii. So first is atomic radii. So what does this mean? An atomic radii, it means the size of the atoms. So here, this atomic radii, it has been classified into four types. So what are the four types? One is the covalent radii, other is the metallic radius, the van der Waals radius, and the fourth one is the ionic radius. So this overall, they are the four types of atomic radii that we will be dealing with. So first is the covalent radius. So how do we define a covalent radius? A covalent radius, it is defined as half of the distance between the two nuclei. Supposing we have a chemical bond between two atoms. So the covalent radius, it will be given as half of the bond length or half of the distance between the two nuclei. That is, supposing we have a diatomic molecule such as F2Cl2 Br2 or I2, then the covalent radius, it will be given as half of, suppose for fluorine, it will be given as half of the radius of the distance between the two nucleus atoms, between the two nuclei. This is how we measure the covalent radius for a homonuclear diatomic molecule. Now if we have a heteronuclear diatomic molecule, that is of the type AB, so here then the bond length, first we will calculate the bond length. Here it is equal to the sum of the covalent radii of A and B. That is, the RAB will be R of A plus R of B. So that is how we calculate the covalent radius of a homonuclear and a heteronuclear diatomic molecule. Now then, this is not very easy to calculate, because once we consider the difference in electronegativities, so here there will be, so we will be using this formula. Supposing this formula, it was actually proposed by Shoemaker and Stevenson, and this actually takes into account the difference in electronegativity. So here it will be given as R of the radius of AB molecule will be given as radius of A plus radius of B minus 0.07 chi of A minus chi of B whole square. So what is this chi A and chi B? They are the electronegativities of A and B molecules respectively. So there are certain scales to measure the electronegativity. There are certain procedures by which we can calculate electronegativity that we will study later. But this is how in general we calculate the covalent radius. Now coming to this, here in table 1.7, here there is a list of different covalent and van der Waals radii of the elements of the different of the elements that has been shown here. As you can see, here it is presented for all the elements. Now there is one very important inference or conclusion that we can say: the van der Waals, the values of van der Waals radii, they are larger than that of the covalent radii. Because why the van der Waals radius is much larger than covalent radius? It is because we know that van der Waals forces, they are very weak in nature, and thus they are much weaker than the forces that operate within the atoms in a covalently bonded molecule. So that is how, why we see, since they are very weak in nature, so the radii, they spread to a large, the forces of interaction, they operate to large distances, and that is why they become, the values are large. So here in figure 1.3, in this figure, the covalent and van der Waals radius of solid chlorine, it has been shown to you. So first, how do we know which one is the covalent radius and which one is the van der Waals radius? So the distance between the nucleus X and the X dash of the two non-bonded neighboring chlorine atoms. Here the distance between X and X dash, it represents the van der Waals radius of the chlorine atom. Now we know that van der Waals radius, it implies the point of the closest approach between two molecules. So here we can say this gives us the value of the X and X dash, it gives us the value of the van der Waals radius. Whereas if we take the distance xy and divide it by half, then it gives us the value of the covalent radius. So that is how we can calculate the van der Waals radius and covalent radius of a particular ion that is given to us. So here from this figure we can say that van der Waals radius, it is an indication of the distance of the closest approach of one atom with another atom, but it is not covalently bound to it. But the covalent radius, it gives us an idea about the covalent bonding or the distance between the two nuclei of the bonded atoms. So then we will talk about the metallic radius. So metallic radius, it is defined as one half of the distance between the nuclei of two adjacent metals. Now for a, as we have calculated the covalent radius, similarly when two metal atoms, they bonded, then the half of the distance between the two nuclei of the metal atoms, they give us the value of the metallic radius. Like for example, the internuclear distance between two adjacent sodium atoms in a crystal of sodium metal is 383 picometer. So the metallic radius here for sodium will be 382 by 2, that is 191 picometer. So that is how metallic radius, it gives us the distance between two metal atoms that are packed inside a lattice. Then comes the ionic radius. So here ionic radius, it is defined as the distance between the nucleus of an ion and the point up to which the nucleus has an influence on the electron cloud. So here this distance, we do not have to divide it by 2. It will just measure the distance of between the nucleus of an ion and up to which the nucleus can feel the influence on the electron cloud. So all we know that all common cations, they are smaller than all common anions except for rubidium and cesium, because they are the largest cations and they are larger than oxide and fluoride anions. So fluoride and oxide anions, they are the smallest anions. So in general, we see that the cations, they are smaller and anions, they becomes larger. So now here in general, so here we can see that there is a decrease in size from anion to covalent radii of corresponding atoms to cations. So whenever we have a series of isoelectronic species, suppose here in this example, like N3 minus, O2 minus, neon, Na plus, Mg2 plus, here in this they are all isoelectronic species. So when we have a series of isoelectronic species, the greater is the effective nuclear charge, then the smaller is that species, that particular ion it contains, it has the smallest size or the radius among the all. Now we know that the alkali metals, they are the largest in their corresponding periods in the table. So when we move across a period, so we know when we start with the second period or the third period, it is mostly known that the alkali metals, that is the group 1 metals, they have the largest size in that particular period. So here, but the size of the atom or the ion, it decreases when we go, decreases when we go across the period, but it increases when we go down the group. So this is a very common phenomena that we see, that when we go down the group, the size of the atom or the ion, it decreases. sorry, when we go down the group, it increases. So this is why, because we know that there is an addition of extra orbital as we move down the group. So now this addition or the presence of this extra shell of electrons, it increases the effective nuclear charge, and thus the size increases. For particularly, as we see for the group 1 elements, the size, it increases, and particularly this has been marked for group 1 and group 2 elements. Then similarly, the atoms of the alkaline earth metals, they are smaller than that of the corresponding group 1 group elements. So group 2 elements, when we compare a particular group 2 element with a group 1 element, then we know that the alkaline earth metals, they have a, the size is actually smaller than group 1 elements. Now why this happens? This happens because of the increase in effective nuclear charge that increases with atomic number. So now due to this increase in effective nuclear charge, the valence electrons, they are pulled more tightly to the nucleus. So as they are pulled more closely to the nucleus, then there is a reduction in their size. So that is why here the atomic radii or the ionic radii, they are smaller than that of the group 1 elements. So here in table 1.8, different metallic and ionic radii of elements, they have been listed here, and we can see the different types of comparisons. So the trend in the variation of the metallic radii in the alkali, alkaline earth and transition metal value here that we have seen above, it has been shown in figure 1.4. So this is how the trends in the metallic radii of different elements, like they are present in the group 1, group 2 and transition elements, here it has been shown here. So as you can see, so for this group 1, it has been shown here. For period 4, 5 and 6, it has been shown here. So here we can see that as we move from alkali metals, like that is for the group 1 elements, to alkaline metals and followed by the transition metals, then the radius, it decreases very sharply. But when within the transition elements, although the radius decreases, but the decrease in the radius is not very sharp, as it can be seen from alkali metals to alkaline earth metals. Now this is a very interesting observation, because now we know that for transition elements, the electron, it enters into the d orbital. So here, why this particular this observation, and it is this observation is more prominent in the second and third row transition series. Here this has been explained for the particularly for the first row transition series. It has been explained that as the number of the as the extra electron, it goes into the d orbital, then due to inter-electronic repulsion, there is a gradual increase in size. So here, that is how it is explained. So now there are various factors that affects the atomic radii. So the two first of the important factors which influence the atomic radii, the first is the principal quantum number, or that we represent it as small n. So as the principal quantum number increases, then the outer electrons, they go farther away from the nucleus. So as they go farther away from the nucleus, thus the atomic radius, it increases. So hence n is a very critical factor that influences the atomic or the ionic radius. The second factor that influences the atomic radius is the effective nuclear charge. So what is this effective nuclear charge? So this is defined as the impact of the pull of the nucleus on the electrons. So the magnitude of effective nuclear charge, it determines the magnitude of the force of attraction exerted by the nucleus on the outermost electrons. So now the greater the magnitude of the effective nuclear charge, then the electron, it experiences a greater force. So hence, as a result, as the electron, it experiences a greater force, it is pulled inward by the nucleus, and hence the atomic size is decreases. So that is how effective nuclear charge, that is represented as Z star. It is very crucial for determining the atomic radius. So the effective nuclear charge, it is the amount of positive charge felt by the outer nucleus that is present in an atom. It is always less than the actual charge, that is the Z of the atom. The effective nuclear charge felt by an outer electron, it depends upon the actual nuclear charge and the type of the screening electrons that are present in between. So here mathematically we can write Z star, or the effective nuclear charge, it is given as Z minus S. So here this S is called as the shielding constant. Now this shielding constant, it is estimated with the help of a rule, and it is called as Slater's rule. So Slater developed this rule, and once we know the value of this Slater constant or the shielding constant, then so we can find out the value of the effective nuclear charge, or the Z star. So now how can we calculate the shielding constant? So there are certain rules which we need to follow for calculation of the S. So this is a very common rule that that is quietly followed for the calculation of S. So first, to begin with, we can first we will write the electronic configuration of the element. Suppose we are considering a particular element, then we will write the electronic configuration in the open format, like it has been shown here: 1s, 2s, 2p, 3s, 3p, followed by whatever its configuration is. Then we will classify them into smaller and higher categories depending on their ns and np value. So here, like for example, we will consider titanium. Here the electronic configuration for titanium, it is given as 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and 4s2. So first we write the open electronic configuration of titanium atom. Then we see the two electrons in the 4s orbital, it will contribute nothing towards the screening constant for the electron in the 3d orbital. So here this 3d 4s, since it is filled, so they will have no role in the screening of the 3d2 orbital. So the screening here, we will now calculate the uh, electrons that are present in ns or np orbital. So all other electrons here, they contribute s is equal to 0.35 each, except for 1s, which contributes capital S is equal to 0.30. So for ns, that is in this case, we will contribute here, n is here for 0.35, and suppose we have an electron which is present in 1s, it will contribute 0.30. The electrons in the n minus 1 shell, it will contribute s is equal to 0.85, and the electrons in n minus 2 or below, it will contribute s is equal to 1 for each electron. Now then we will consider an electron for an nd or nf orbital. So all electrons in nd or nf, they contribute s is equal to 0.35, and those electrons, they lie lower than nd or nf, they contribute s is equal to 1. So like here we will come to an example. So we will consider the Z star for an electron in K and zinc atom. Now we know potassium, it is 19. So first we will write the electronic configuration. That is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now here we will group them. Here 4s is not fulfilled. 4s is single. So that is why the total value here will be for 4s. Here we will start with, we will contribute, here it is 0.85, here it is 83, it is written, it is 0.85 into 8. We will consider for the ns and np. So here 6 ns and np is 6 plus 2 is 8. So here it is 8, and below that we will consider, here below it will be 1 into 10. So we get 16.8. Then here z is 19 for potassium, so 19 minus 16. So similarly, this is how we can calculate for other atoms. So this is how we calculate the effective nuclear charge, or Z star. So here in table 1.9, we have different elements along with their Z, the shielding constant, and the Z star values for the first 30 elements. It has been given here. Then now coming to periodicity in atomic radii. So we were talking about the general trends in atomic radii. So here we have talked about the variation of atomic radii down a group. So now we will consider the periodicity in atomic radii. Two general periodic trends are found for all types of atomic radii. So first is the atomic radii. It decreases along a period that we know, and it increases down the group. This is a general observation. These changes in effective nuclear charge and the principal quantum number in the periodic table also influence the atomic radii. So here period variation of covalent radius with atomic number, it has been graphically, it has been shown here. So here when we look into this table 1.9, here it has been shown here the different z star values. So there is a steady decrease in the value of z from alkali metals to halogens for the period 2 and 3, but there is no change in the value of n because all the element they go to the principal quantum number. So as a result, there is a steady decrease in the covalent radius from 123 and 156 picometer from lithium and sodium to 64 and 94 for chlorine and respectively. But when here, if we for lithium to here we can see, but the decreased covalent radii, when we go across a transition series, here it becomes much smaller. Here that it is, we see that there is a steady decrease, but the decrease in covalent radii across the transition series is very much smaller, because across the transition series there is a very small increase in effective nuclear charge, and that is almost by 0.15 units. So since this unit is very small, so there is also a very the decrease is very slow. And then particularly coming to the lanthanide series, here we know that the filling occurs in the f orbitals. So here the filling happens in n minus 2f, plus it also undergoes the influence of the effective nuclear charge. So what happens here is the electrons in the n minus 2f orbitals, they shield the ns electron, which largely determine their size, and from the increase in
ठंडा
nuclear.
प्राणी मोबाइल लिया रे बोला ईद पना की प्रशंसा करा है
Okay, so now we're talking about lanthanide. This is because of the lanthanide contraction. So the lanthanide contraction, what happens here is it cancels the effect of the last shell that is added in the sixth period, and therefore what happens is because of this lanthanide contraction, the transition elements in the 4D and 5D, they have almost the same radii. So this is how the effective nuclear charge, it influences the different types of the radii of the different atoms. So here in figure 1.6, the ionic radii of M2 plus ions, it has been shown. So here, because of the radius of the for the particularly for the 3D metals, we know that the 3D metals, they form different types of complexes. Because of the change in such type of radius of these metals, then we can find they form high spin, low spin, and different types of complexes. Then coming to atomic volume and density. So there are two general trends
मेरे
that
भाई
is observed.
ऊपर से
See, guys, please keep your mouth. Please keep. I just please don't disturb. Keep your mics off. Then coming to atomic volume and density. So there are two general trends that are observed in the density of the elements in the periodic table. So in general, there is an increase in density because of the increase in atomic mass and decrease in size of the atom. So here, this is a general trend that along the period there is an increase in density, because we know because of the increase in the atomic mass and decrease in size of the atom. So here in a particular period, the alkali metals, they have the lowest density. Considering the solid element structures, they are often the same without any group. So here when we look into from table 1.1, we found out that the density of potassium, it is less than that of sodium. So thus potassium, it becomes an exception to this trend. The alkali earth metals, they are denser than the group 1 metals because they have two valence electrons per atom for bonding the electrons into a metallic lattice. The density decreases slightly on moving down the group from beryllium to carbon, but increases considerably thereafter up to radium. The size of an atom of an element is also related to its atomic volume. So their trends are the same. Similar density is also related to the size of the element. So when we move across a period, as the size decreases, the density of the element, it becomes higher. So this is a general trend of increasing density when we move across the transition series. For the 4D and 5D elements, this increase is not that regular as the increase in densities for 3D elements. So this, the increase in density in the D block is much higher than that what is observed in the S and P blocks. So when we go down the S and P blocks, the size of the atoms, we know increases when we move down the group. So because extra shells are added. So now the elements in the first group of the D block elements, they show the expected increase in size. But as we go to the subsequent groups, there is an increase in radius between the first and second member, and there is a very little increase between the third and fourth member, and this is mostly because of the, we can see lanthanum and hafnium, where we can see due to the presence of the lanthanide contraction and the lanthanoid series, we see such low differences. Here in the trend in densities of the alkaline earth metal and transition metals of the fourth, fifth, and sixth periods, here it has been shown. For period 4, we can see for period 4 and 5, here we can see the gradual change, but for period 6, we can see the large change in atomic densities. There is a gradual decrease in the size of 14 lanthanoids, that is from cerium to lutetium. This is called as lanthanoid contraction. So this lanthanoid contraction is particularly responsible to the different variation in the elements of the lanthanide series, but we do not, because of this contraction, with the proper, there is the difference between the properties between the first row and second row transition series, they are much larger but than that of the second and third row transition elements. So that is why lanthanide contraction plays an important role in deciding the atomic volume and atomic density of the transition elements. So now we will talk about the melting and boiling points. The alkali metals, they are soft and can be cut with a knife. So we know sodium metal, it can be cut with a knife. So as a result of the increase in size and repulsion of the non-bonded electrons, the cohesive energy and the tendency for metallic bonding decreases. So as we go down the group, then the softness, it increases as we go down from lithium and cesium. So these metals, they have low melting and boiling points. The group 2 metals, they have higher melting points when we compare them with group 1 metals, and the reason is because group 2 metals, they contain dications, that is +2 charge on them, which causes them to be more strongly attracted to the electrons, making it difficult to be separated from one another. So here the melting and boiling point of the transition elements, they are generally very high. The transition elements, they typically have a melting point of more than 1000 degrees centigrade. So however, there are also few exceptions like lanthanum and silver, they melt at below 1000 degrees centigrade. Others we have like zinc, cadmium, and also mercury, which is a liquid at room temperature, and the melting point is -38 degrees centigrade. So here the high melting point, they are in contrast to the low melting points for the S block element. So when we look into the low melting point of the S block element, that is for lithium and cesium, for lithium it is 181 and for cesium it is 29. In comparison to them, the transition metals, they have a very high melting and boiling points. So the melting points of the transition elements, it depend upon the strength of the metallic bond, which increases with the availability of the electrons to participate in the bonding. So we know that between calcium and scandium, so there is a jump of nearly 700 degrees in the melting point. So why this happens? Because we know calcium is 20, the atomic number of calcium is 20 and scandium is 21. So there is an addition of an extra electron, that is 3d1 in scandium. Now with this addition of 1 ampere day electron, it increases the interatomic forces, and therefore the increase in the metallic bond, which gives us high values of melting and boiling point. So this is how we can see between calcium and scandium the difference in their melting and boiling points. Now however, we cannot generalize this behavior, because when we move across any period, then the value of the melting point, it first increases, and when we reach the middle of the transition series, it decreases. So like for there, this is a very typical behavior if we consider the first transition series. So like from scandium to manganese, it increases, but after manganese, then it decreases. Now there is also a very reason for this, is that zinc, cadmium, and mercury, here the electrons are paired up in these atoms. So once they are paired up, the melting points, they are comparatively lower, and this trend of the first increase and the decrease is also seen in the second and third transition series. Then coming to ionization energy. So first we will define what is this ionization energy. So here in general terms, we can say that ionization energy, it is defined as the energy that is required to remove a loosely to bound a strongly bound electron from an isolated gaseous atom in its ground state. So here what does this mean? So this means that we have an element, that is M. We will take out an electron from its gaseous state, isolated gaseous atom, that is M plus G, and it will release the amount of energy. So the amount of energy that is released here, it is called as the ionization energy, or sometimes it is called as ionization potential. So here the ionization potential is always the amount of energy that is released. Now when for particular cases, when we can remove two or more ionization energies, then we can say that it is called as the, when one electron is removed, it is called as the first ionization energy. When we remove two electrons, the amount of energy that is required, so here that is also, it is called as a second ionization energy, which gives us first M for being M plus, then M plus after removal of another electron, it gives us M2 plus. So likewise, these are called as successive ionization energies. And the mostly the common unit, SI unit for ionization energy is kilojoule per mole. So the ionization energy of an outer valence electron, it is related to the effective nuclear charge felt by the electron, and it is given by the formula I is equal to Z star, that is the effective nuclear charge, into E square by 2 1 by R into average. So 1 by R is the distance of the electron from the nucleus, and here 1 by R average is the average value of 1 by R. So once the higher is the effective nuclear charge that is felt by the electron, then more energy will be required, and thus the ionization energy will also be high. So here if an electron is present very far from the nucleus, then a low energy will be required to remove that electron from the nucleus, and thus the ionization energy will be very low. So for also, when we take the case of completely filled or half filled orbitals, we know that they are more stable, and thus these removal of electrons from completely filled or half filled subshells, they require more energy. So these are some of the cases how we will determine the ionization energy. The valential electron configuration of particularly noble gases, we know that noble gases, they are highly stable in nature, and that is why their ionization energy, that is, it is very high, and it is because since it is very difficult to remove an electron from a noble gas configuration, and that is why when we move across the period, the last atom is that of a noble gas, and they have the highest ionization energy in the respective periods. Then coming to periodicity in ionization energy across periods. So we will now look into the variation of ionization energy across the period. So here in table 1.10, we can see the ionization energies across a period for different types of elements. So here the variation of ionization energy or group, here it is shown best. We can, without just by looking at this period, we cannot come to a proper conclusion. That is why we have, mostly it is plotted a graph. Here in figure 1.10, you can see this is the variation of ionization energy with respect to atomic number. The ionization energy is taken in the y-axis and the atomic number it is given in the x-axis. Now here we can see the variation of different elements of the with respect to ionization energy with respect to atomic number. So first here is the group 1 elements. We know that they have the electronic configuration of the preceding noble gas. So they have a very, we know mostly they contain s1, the last electron it goes to the s1 orbital. That is why they have this tendency to easily give up this single outermost electrons to form the univalent cations. Like if we consider sodium, so sodium is 11, so it has this tendency to always give up its electron to form Na plus. So their first ionization energy are the lowest in the respective periods, so they are the most reactive of the metals. Now when we go down the group, we know that as we go down the group, the atomic size increases, thus the ionization energy it decreases, because as the electrons the size increases, the electron is added to the farthest cell. Now as the distance between the nucleus and the outermost electron increases, thus the ionization energy it decreases. So thus, as the ionization energy decreases, the elements which are present at the end of the group, they resulting in an increasing in their reactivity. The effective nuclear charge they felt by the electrons, it increases after the removal of the one electron. Now we see, after one electron has been removed from group 1 elements, then the removal of the second electron it is very difficult. Why? Because in the case of this Li plus and Na plus or K plus, they have the stable electronic configuration. That is why when once they have this stable electronic configuration, particularly of a noble gas, then the removal becomes extremely difficult. That is why when we see group 1 metals, they mostly form univalent cations, that is Na plus, K plus or lithium plus. So this is how the ionization energy it vary in group 1. So now we know they have the highest electropositive character or metallic character. So here we also see that the metallic character it increases as we move down the group from lithium to cesium. So now also the rubidium and cesium they are so electropositive that they emit electrons just when they are exposed to light. So this property is that since they become so reactive, or they have this tendency to give up the electrons so easily, that when they are shown to us light source, they emit electrons, and this property is called as photoelectric effect. Then the first ionization energy of alkaline earth metals is more than that of the corresponding metals. Now, corresponding alkali metals. Now we know that for group 2 elements, the electronic configuration is Ns2. That is, the last electron it enters the Ns2 orbital. So here it has this because the size is smaller than the group 1 elements. So the second ionization energy of these elements is almost twice their first ionization energy, because once after an electron has been removed from the orbital, the effective nuclear charge increases, so that the remaining electrons they are held more tightly. So that is why more energy is needed to remove the second electron. But in these elements, their second ionization energy is less than that of the corresponding alkali metals because of the stability of the closed cell configuration. So the lower second ionization energy of the alkaline earth, we can take an example. Here in figure 1.10, it shows the first ionization energy of the first of the elements of the first 6 periods against their atomic numbers. The first ionization energy generally increases from alkali metals to noble gases across any row of the periodic table, but the increase is not perfectly regular. Here we can see. Now we know that in that across any row of the periodic table, the effective nuclear charge it steadily increases and the atomic radii decreases. Now these two effects they combine each other to form the ionization energy across the period. So thus the ionization energy of the alkali metals they are the lowest, and those of the noble gases they are the highest when we move across a period. Like for example, in the elements of period 2, in spite of an increase in the Z star value and decrease in R, the first ionization energy of B and O, they are lower than that of BE and N. So some anomalies they have been observed. So because when we look into beryllium, the outer electron is removed from the filled 2s orbital, whereas in boron the electron is removed from the singly occupied 2p orbital. The 2p subshell it is higher in energy than 2s, so the 2p of electron it is more easily removed than that of a 2s orbit electron of beryllium. So thus looking into the electronic configuration we can actually say which requires more ionization energy or where less ionization energy is required. Then coming to trends in ionization energy down the group. So we know down the group the effective in the particularly in the S and P block elements, there is a general increase in the atomic radius because the principal quantum number it increases. Thus the dominant factor in determining the ionization energies of the elements on moving down the groups is their atomic radius rather than their effective nuclear charge. So now as expected, as the principal quantum number it increases, the first ionization energy decreases down the group in the case of main group elements. But in the case of transition elements, opposite trends are observed. The first ionization energy of the corresponding 3D and 4D series they are almost similar, but these are smaller than the first ionization energy of the 5D elements. So all this the values of ionization energy is largely dependent on the hello. Coming to trends in successive ionization energies, so we know that successive ionization energy it means the removal of the second, third, fourth, or fifth electron from the elements. So here the different successive ionization energy of first 20 elements they have been shown here. Now the successive ionization energies of an element it becomes larger. Why? Because the removal of electrons it now becomes difficult, because as once we remove from the nearest shell that are lying close to the nucleus they require more energy. That is why the removal requires more energy. So the difference between successive ionization energy of the same element it is not constant. So big jumps we can see they occur whenever an electron of lower principal quantum number is removed from the first time. Like for example, alkali metals, the second ionization energy are much higher than the first. For alkaline metals, the third ionization energy they are higher than the second, and for the halogens, the eighth ionization energy are much greater than the seventh. However, these cannot be explained on the basis of in nuclear charge alone. There are other important factors which also contribute to the variation of the successive ionization energies. Now we'll start with electronegativity. We'll just take a break of 5 minutes and again start with this electronegativity. So the next parameter that we will talk about, which influences the different periodic properties, is electronegativity. So first we will define what is this electronegativity. Electronegativity, it is defined as the tendency of attracting the electron pair towards itself by an atom, and it is mostly, it was discovered by, it is not a directly measurable physical quantity, but it is a theoretical concept, and we had, there have been different scales by which we calculate the electronegativity of an atom. So this concept, it was first developed by Pauling. So this was defined on the basis of the patterns, where, that is, we have a basis of the patterns derived from the energies of the thermochemical data, like the mathematically here it has been given as EAA, that is the bond energy for the formation of diatomic A2 molecule, and EBB is also the bond energy for the BB diatomic molecule. So the excess bond energy, that is given as EAB minus root over of EAA into EBB. It is due to the electrostatic attraction between the partially charged atoms. That is, suppose we have a, it acquires a slight delta positive charge, and B, it acquires a slight delta negative charge. Then the X here, it is given as 96.49 into chi A minus chi B whole square, where chi A and chi B, they are called as the electronegativity of the elements A and B, or in general we can write it as delta chi of AB molecule. It will be given as the bond energy of AB molecule minus root over of bond energy of A2 into root over of bond energy of B2 divided by 96.49. So this is how we calculate the electronegativity difference as per the Pauling scale. So here the largest electronegativity difference on this scale between the most electronegative element, that is fluorine, and the most electropositive element, that is cesium, it came out to be, using
Ma'am,
this
by
formula,
using this
it came
formula,
out to be
exactly we can
3.3.
calculate the electronegativity difference between A and B, because del X chi AB is here. That means it is the electronegativity difference of the bond. But how we can calculate exactly the electronegativity of A or B element?
That can be calculated by another formula, that is by Mulliken scale or the Alred-Rachau scale. So here it will give you for the bond only. So chi A and chi B, here using this Pauling scale, here it will just gives us the difference in electronegativity. We cannot find out the Pauling scale, we cannot find out the chi of A or chi of B. For that, other scales, they were improvised. This scale was modified. So here then, like, the difference between fluorine and cesium, fluorine is the most electronegative element and cesium is the most electropositive element. The difference came out to be 3.3. So here, so then an arbitrary value of maximum value of 4 was applied. Pauling, he assigned an arbitrary value of 4 for fluorine, so that the electronegativity of all elements, it remains positive. So that is how this Pauling used the above formula for calculation of differences in electronegativity for a particular compound rather than a particular element. So then this formula, it was improvised, and then Mulliken, he further improvised this formula and he gave a very simple formula. Chi of A for an element A, it will give you, it is calculated as the ionization potential of A, plus it gives the electro here, it is the electronegativity chi here, both for the E of A by divided by 2. So now here both these values are positive, and then this value is much easy, this formula is much easier to access. But the electronegativity value, the maximum electronegativity value on Mulliken scale, they are about 2.8 times higher, that is approximately 3 times higher than those of the Pauling's values. So this is how Mulliken scale is used. Then an improved formula was provided by Alred and Rochow. So he gave us that, both these scientists, they gave us that electronegativity can be, it is equated to the force of attraction between an electron and an atom that is separated by a distance which is equal to the covalent radius, and that is how the numerical relationship here, it is given as chi of A is equal to 3590 Z star, that is the effective nuclear charge, by R square, that is the covalent radii whole square, plus 0.744. Now this method, we can see it has an advantage that it can be applied to a comparatively large number of elements. So this is the has a broad applicability rather than Mulliken and Pauling scale. The Alfred-Rachau scale, it is most preferred because its scope is wider and applicability is large. So here in table 1.212, other various different types of the electronegativity, the Alfred-Rachau electronegativity, it has been shown. So all the electronegativity scales, they give average values of electronegativities of the elements in different bonding environments. So the larger the difference between the electronegativities of two elements, then we can conclude that the bond is more polar between these two elements. So then coming to the periodicity in electronegativity, the electronegativity values of elements, they show a fairly discernible periodic trend throughout the periodic table. It is mostly similar to that of the ionization energy. So now thus expected, the electronegativity of the element, it increases sharply for the rows of the S and P block elements, because the effective nuclear charge of these elements, it increases sharply. Like when we consider move from lithium to fluorine, we know that the effective nuclear charge, it increases very sharply. That is why the electronegativity also increases. But when we move across a transition element series, then the increase is, although it increases, but the increase is much slow. Now why? Because we know that the addition of an extra electron in the transition series, it provides a good shielding effect, because the an extra electron, it is added to the d shell, and that is why it provides relatively good shielding for the outer electron from the nucleus. So when we move down a group of representative elements, in the lithium group, there is a general decrease in electronegativity. Now, this decrease is relatively small except between the first two elements. The much greater electronegativity of the lithium row elements, it correlates well with their small size. Now, as expected, the elements of period 4, that is from gallium onwards, they have greater electronegativities than would be expected by extrapolation from values for the first two elements. Now, we know that because of the presence of or the addition of transition elements, the nuclear effective nuclear charge of these elements is greater than that if they were not present. Now, transition elements, they have very fairly low values. It increases from scandium to copper with a fall at manganese. From scandium to copper, from 21 to 29, we see what happens is from 21, that is scandium, it occurs a fall at 25, that is manganese, and then up again at zinc it falls. So but this increase in electronegativity is very small, because the extra electron that is added, it goes to an inertial, which provides good shielding to the from the nucleus. Now thereby the elements, they become slightly less metallic, and if we look into this M2 plus and M3 plus values, here we can see the variation of the difference in the electronegativity for the, and for particularly for the transition elements, we see that the difference is not much large. Then is electrode potential. Now, what is electrode potential and how does it affect elements in a period? We will discuss its periodicity. So now when we take a metal and we place it in a solution of its own ions, then a potential is difference is set up between the metal and the solution. Like what do the whole concept here, it has been shown pictorially. So that is, we take a metal M, and then we take the solution of the same metal M, and then what happens is, if we apply electricity, we see that a potential difference is gradually it develops between the metal and the solution. So the value of this potential difference for a particular metal, it depends upon the metal only, the concentration of the metal ions in solution, and most important is the temperature. So now by convention, the potential difference set up in a 1 molar solution of metal ions at 298 K, that we call it as the standard electrode potential. Now, measuring the standard electrode potential, it is extremely difficult or it is almost impossible. So, it has to be measured against some standard reference, and that standard reference is the hydrogen electrode, or what we call it as the SHE, the standard hydrogen electrode. So, this standard hydrogen electrode, it consists of hydrogen gas when the pressure is 1 atm, and that is in contact with 1 molar solution of its ions at 298 K. So the values of some standard electrode potentials for the first elements of first transition series, they are given here, they are shown in table 1.3. Here you can see for titanium, vanadium, and the difference, the E0, the values, it has been shown here. The electrode potential is a measure of the electropositive character, and mostly it implies the nature of the reactivity of these metals. So we find that along a period, generally there is a decrease in electropositive character, and thus there is a decrease in reactivity of the metals. When we look into table 1.3, the thermochemical parameters also say the same thing. Now here if we look, we see that all the elements of the first transition series except copper, they have negative values, and thus they can react with acids producing hydrogen. So here I plot a variation of the electrode potential. Here it is shown in figure 1.13. So now we can see this unique behavior of copper, which because copper has a positive E0, thus it cannot liberate hydrogen from its acids. So only oxidizing acids, that is, they react with copper, that is nitric acid, and it should be in hot concentrated nitric acid. So the high energy to transform copper to copper 2 plus is not balanced by its hydration enthalpy. So the general trend is that the towards less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. Now also we have certain elements which do not follow this trend. So then coming to oxidation states. The transition elements, they usually exist in several different oxidation states, like for iron. Iron exists in two oxidation states. One is Fe2 plus, that is the ferrous, and the other is Fe3 plus, that is ferric. So similarly, we come across a mostly those transition elements, they show variable oxidation states. Now, why do mostly transition elements they show variable oxidation states? This is mostly related to their electronic structure. Now, when we look into the electronic structure, we can look into the number of d orbitals that are present in them. So by the giving up different types of the number of d or electrons, then they show variable oxidation state. Like for example, for here in table 1.5, we will consider chromium. So chromium here, it shows two oxidation states, that is +2 and +3. But when we reach manganese, 5 different oxidation states are possible. Similarly, when it has been assumed that the element that is present at the center of the transition series, it shows the maximum number of variable oxidation states. So, but here, as we from beyond manganese onwards, we see the number of variable oxidation state decreases. So why this tendency, it is trend it follows? This could be due to the steady increase in the effective nuclear charge along the series, thus pulling the d orbitals into the electron core and thus not making them available for bonding. Like for example, if we consider zinc, for zinc only one oxidation state is possible, that is zinc +2, where no d electrons is involved, because we know zinc is highly stable, and here we cannot, it is very difficult to remove an electron from the d orbitals, stable fulfilled d orbitals. On the other hand, it is difficult to form species that do not utilize d electrons. Like for scandium +2, it is virtually unknown, and Ti +5 is more stable than Ti +2. So thus, by looking into the number of the d electrons, we can say, because of the variation in the d electrons across the 3D series, we can say the transition elements, they show variable oxidation states. Now, when we look into table 1.15, here it has been shown, we can see that the trend in the oxidation states as we go down the group. So when what happens here is the trend in the stability of the oxidation states is different for the transition elements and the main group elements. That is, for the main group elements, the higher oxidation states, it become less stable as we go down the group because of an effect that we call it as the inert pair effect. However, when for the transition elements, the stability of the higher oxidation state, it increases going down the group. So now, to exemplify this, we will consider group 6. Now, group 6, it is composed of chromium, molybdenum, and tungsten. We have seen that chromium has +6 oxidation state in potassium chromate. It is a good oxidizing agent, forming Cr+3 as the product. So here Cr+3, it means that in many cases Cr+3 is more stable than Cr+6. Whereas in contrast, molybdenum and tungsten in +2 oxidation state, they are not easily reduced. So this implies that the lower oxidation states, that is Mo+3 and tungsten+3, they are not easy to form as easily Cr+3 is formed. Thus, the stability of the +6 oxidation state for the group 6 element will be tungsten, molybdenum greater than chromium. So with this trend is also found for group 4, which consists of titanium, zirconium, and hafnium. So thus we can see that various oxidation states, they react to various types of various environments of oxidation and reduction. Then the highest oxidation states, they are often stabilized in the oxide and the fluoride compounds like MnO4 minus, CrO4 2 minus, VO2 plus, VF5 minus, so V5, etc. So here in these compounds, if we look, the O2 minus and F, they are difficult to be oxidized by the central metal because here the O and F are strong oxidizing agents. So here's the reactivity of some oxidation states of first transition series elements in aqueous solution. It has been shown here. These are the reducing agents and the most stable states have been shown here. Now, once the D5 configuration is reached, that is beyond D5, that is from D6 to D10, the tendency for all the D electrons to participate in bonding, it gradually decreases. That is, suppose we say iron. So iron has a maximum oxidation state of +6. However, the second and third elements in this group, they attain a maximum oxidation state of +8, like in RuO4 and osmium tetroxide. But the difference between Fe and the other two elements, why this difference arises, it is because of the increase in the size of the atoms. The oxidation states, they form a regular pyramid. Then the oxidation state number of all the elements in the elemental state is 0, plus several of the elements, they have zero valent and other low valent states in complexes. So the higher oxidation states, they are displayed with electronegative elements, mostly like oxygen and fluorine. The compounds in higher oxidation states, they are oxidizing in nature and covalent, while those in lower oxidizing states, they are reducing and ionic. So these are different factors that influences the stability of different oxidation states. Then the stability of various oxidation states, that is mostly for manganese, iron, and copper, they are mostly explained by certain diagrams, and those diagrams, they are called as Latimer diagrams. So Latimer diagrams, they are based on electrode potential and they show the different species of an element in their varying oxidation states. So now here the oxidation state, we can here for a particular Mn case, here we have an example. It has been shown for Latimer diagram for manganese in 1 molar acidic solution at 25 degrees centigrade in oxidation state from +7 to 0. Here it is shown. Now this whole series, this whole step is called as the Latimer diagram. Now here, if we start from the left hand side, it is MnO4 minus. The oxidation state of manganese in this ion is 7 plus. Then when it gets converted to MnO4 2 minus. So here, if we look here, then the oxidation state of manganese is 6 plus, and it requires for this conversion, and the electrode potential is plus 0.564 volts. So in the subsequent step, MnO4 2 minus to MnO4 3 minus, we see there is a change in oxidation state, and the oxidation state here for manganese it was 6 plus, and here it is 5 plus, and this is the electrode potential is plus 0.274. And likewise we can see the change in the electrode potential with the successive change in the oxidation state of manganese. So this is how a Latimer diagram is useful. So the Latimer diagram, it has the standard potentials for redox reactions of element. Now the last part, we will look into the last part which connects Mn2 plus and Mn. Now if we look here, the half cell reaction here, it can be written as Mn2 plus. It takes up two electrons to form Mn 0 here, and the half cell reaction here, it is E0 half, it is given as minus 1.18 volt. Now here again if you look into Mn4 plus and Mn plus 3 here, so just here the half cell reaction, it requires Mn, the hub is E0 half is equal to plus 0.95 volt. Now using this we will calculate the standard electrode potential for non-adjacent species. So these two, the 7 to 6, 6 to 5, these are adjacent species, but 6 to 4 or 5 to 5 plus to 3 plus, they are not adjacent species, they are referred to as non-adjacent species. So now we know that the standard potential values, we know that they are not additive in nature. So how can we calculate? We will calculate by first converting them to delta G0 is equal to minus NFE. So these values are then additive in nature. So like for example of MnO4 minus to Mn2 plus. So here we will consider this MnO4 minus, here the oxidation state of manganese is 7 plus, and then for Mn2 plus, we know the oxidation state here is plus 2. So then how can we calculate the standard electrode potential? So here we will add up the number of electrons, and the here is uh, the electrode potential. So here for 7 to 6 it is 0.56, then 6 to 5 it is 0.274, then for 5 6 sorry 5 to 4 it is plus 4.27, then 4 to 3 it is plus 0.95, and then plus 3 to 2 is plus 1.15. So here the number 1, it represents the number of electrons, and the bracketed terms, it indicates the electrode potentials, and then calculating it, and here this division of 5, it indicates the oxidation change, the change in oxidation. So for like for MnO4 minus, the oxidation state of Mn was plus 7, and here it become plus 2. So the number of electrons that are involved in the process is 5, and that is why it is divided by 5, and the electrode potential comes out to be this. So this is how we calculate the electrode potential for different steps. Now it is also possible to predict whether a species, it will disproportionate into a lower and a higher oxidation state from an inspection of the Latimer diagram. So if the potential to the right of the species is higher than the potential on the left, then the species, it will undergo disproportionation. So for example, if we have M2 plus, it converts to M plus, and finally to M0. Then the disproportionation reaction, we can write it as 2M plus aqueous forming M plus M2 plus. So here the Y volt, here we can see, here it is on the right hand side, and the X volt, it is on the left hand side. So if we subtract the left hand side half cell reaction from the right hand side a Hubsel reaction of the Latimer diagram, then we can write it as E0 is equal to Y minus X. Now we will look into this value of Y minus X. So if this Y minus value X is positive, then the potential of the redox species is higher than that of the left. That is, we have E0 is greater than 0. So once the standard electrode potential is greater than 0, this means that delta G0 is negative, and so the reaction is proportionate. That is, the reaction is spontaneous in nature and the species will disproportionate. Like here for this example, the Latimer diagram for iron in acid solution, it has been given. So how we can know whether here iron is present in Fe plus 6. Here it is 3 plus, 2 plus, and 0. Now we will calculate the change for Fe3 plus to Fe0. And once we find out, after calculation, it has been find out the electrode potential to be minus. So once this here it is greater than 0, so this reaction it is, we can see whether it is disproportionate or not. So in summary, we have talked about different types of periodic properties like atomic radius, ionization energy, electronegativity, the oxidation states of main group elements and transition elements, and different calculation of electronegativity. So here this is about the trends in periodic properties. And these are some of the questions that is associated with this chapter. You can go through these questions. Then coming to the second part of this block, that is the structure of molecules. So here in this structure of molecules, we will be talking about the postulates of Vesper theory, the and predict the shapes according to the Vesper theory. We will understand the Walsh diagram, the d pi p pi plot, Bend's rule, and other geometrical and optical isomers. So we'll start with the valence electron pair repulsion theory, that is the Vesper theory, and it is one of the simplest way to predict the probable structure of a molecules. So this theory, it is based on certain assumptions. The first postulate, it states that the bonding and non-bonding electron pairs in the valence shell of the central atom in a molecule, they arrange themselves in such a way so as to minimize their repulsion. The second postulate states that the repulsion between the two lone pair of electrons is greater than that between a bond pair and lone pair, which is greater than that of two bond pairs. So here, that is, in short, we can say the order can be written as lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. Now here in table 1.1, we can see the basic arrangements of different electrons or molecules according to the Vesper model. So if there are two electron pairs, then the predicted geometry is linear. If the number of electron pairs is 3, it is trigonal planar. If electron play is 4, then it is tetrahedral. And if the total electron pairs is 5, then the geometry is TBP, that is trigonal bipyramidal. And if the total electron pairs is 6, then the geometry is octahedral in nature. Now, suppose in case of molecules with the central metal atom having one or more pair of lone pair of electrons, then we have to use both the postulates. So the first postulates, it decides the location of the electron pairs. That is, it might be both the bond pair and the lone pair. In other words, it determines the electron pair geometry. But the second postulate here, the geometry changes depending on the type of the electronic repulsion. So therefore, the final geometry is assumed by considering the location of the different types of electron pairs around the central metal atom. Like we will consider a common example, that is ammonia. So in ammonia, the central atom N, it contains a total of 4 electron pairs. That is, it has 3 bond pairs and 1 lone pairs. So here, as per number 4, it should be having a total electron pairs are 4. So as per this theory, it should be having a tetrahedral structure. But we can predict that the 3 pairs, bond pairs, it will occupy the 3 corners of a tetrahedron, while the lone pair will point towards the 4th corner of a tetrahedron. But because of the repulsion between the 3 bond pairs and lone pairs, the NH3 molecule, it does not have a tetrahedral structure. But because of this repulsion, the NH3 molecule, it takes up a pyramidal structure. So this is how Vesper theory, it predicts the different types of geometries of the molecule. So here some of the examples it has been given. Suppose there are 5 electron pairs. Out of 5 electron pairs, there are no lone pairs, only bond pairs are present. So the molecular geometry is TBP, that is trigonal bipyramidal. So the common examples are PCl5. Suppose again we consider that there are five number of electron pairs, but here there are four bond pairs and one lone pair. So because of the presence of this one lone pair, then the trigonal bipyramidal structure, it now changes to a seesaw structure here, like it has been shown here. So like for example is SF4 minus SF4. Suppose we have, for when electron pairs is total electron pairs is 5, out of which there are 3 bond pairs and 2 lone pairs, then this the structure that should have been originally TBP, it now converts to T shaped here. And this the structure, it has been geometry, it has been shown here, and the mostly T shaped geometry could be found in CLF3, BRF3, BRF3. Now, suppose we have two bond pairs and three lone pairs, then the geometry is linear in nature, like for XCF2, ICL2 minus. So, similarly, if we consider the total number of electron pairs to be 6, so once if there are no lone pairs, then the expected geometry is octahedral in nature, like it is for SF6 and PF6. Now, when we have there are five bond pairs but one lone pair, then it is square pyramidal in nature. And if there are four bond pairs and two lone pairs, then it is square planar in nature, and common examples are XCF4, BRF4 minus. So now we will look into how to successfully apply this Vesper model to understand the structure of a geometry of a molecule. So first we write down the electronic configuration of the elements. This is, for example, in carbon dioxide molecule, there will be 16 valence electrons when we look into the distribution of 2C and 1O. So this is the representation can be done in two ways. Here 2.1a and 2.1b. So here we cannot predict the bond angle from this Lewis structure. So here now we will consider a structure which will consider all the electron pairs and minimize the mutual repulsion among them. So here what we have to find out, that we will consider the different types of shapes like linear, angular, trigonal, planar, and then deciding on the number of the sigma bonds. And then first we will decide the sigma bonds and then we will give the pi bonds. So here in carbon dioxide, px and py orbitals on the carbon atom, they are unused by the sigma system and they are available for the formation of the pi bonds. So here that is how we can the molecule it approaches. And Vesper theory, by just simply applying this Vesper theory, we can look into carbon, how hybridization occurs and what shape it acquires. So here this has been some simple molecules where the central atom forms bond pair, it has been shown. The molecular orbitals, they approach, undoubtedly it uh, gives us information about the structures, but the Vesper rules, it can be applied in a very easy approach. Now we'll predict the structure of certain inorganic compounds and by applying Vesper theory here, like for example trimethyl chlorine. So the Lewis structure of CH3b, it will trimethyl borane, it will place 6 electrons in the valence shell of the boron atom. We will then minimize the repulsion, then the methyl groups, it should be located at the corners of an equilateral triangle, so which gives sp2 hybridization. The resulting group is D3H. So this is how it will look like. So we will always place the groups in such a way which will minimize the repulsion. Then some other examples that has been shown here for different types of atoms. Then structures of molecules which contains lone pair of electrons. Now we'll specifically look into the molecules that contain lone electron pairs. So first we'll start with H2. So H2 molecule, here the central oxygen atom, it is bonded to two hydrogen atoms and it also contains two pairs of non-bonding electrons. There are four pairs of electrons, that is two bonding and two non-bonding. So each of the four corners of the tetrahedron, they are occupied and they will have any one of the electron pairs. The repulsive forces between the lone pair, bond pair and bond pair, it will now decide the shape of the water molecules. So because of the presence of two lone pair of electrons, so what happens here is then the structure bond angle here is reduced to 104.5 degree, and the shape of the water is bent and not pure tetrahedral. So here we can looking into the lone pair repulsion. Then we can see how this is the molecular structure of methane. Here it is, and this is ammonia, and this is water. So because here we have for water the bond angle is 104.5 degree, and because of the presence of two lone pair of electrons. So now if we follow the second postulate of Vesper, so we can state that the lone pair always occupies a greater volume than the bonding electrons. So the approximate molecular shape along the possible distortions, it can be predicted only if we consider the lone pair. So that is why we have to always consider the lone pair before describing the geometry of any molecule. Now here example is SF4. So the SF4, it has 10 electrons in the valency cell of sulfur, 4 bonding pairs and 1 non-bonding pair. So here the geometry is trigonal bipyramidal. Now we will see the position of the lone pair. So there are two possibilities of arranging this one lone pair, either equatorially or axially. So we have, since only one lone pair is present, these two positions are available with us. So the one with the lone pair in the equatorial position, it is found to match with the experimental data that is that is shown in figure 2.7b. Thus the bonding pairs, they are repelled by the lone pair and bent back, and they form a distorted structure which we call it as the seesaw structure. So this is how the lone pair, it helps us in deciding the or predicting the geometry of molecules. So here, if we look into figure 2.7a, we see that the lone pair has three 90-degree interactions with the equatorial bonding, but only two 90-degree interactions with the axial bonding. So the 120-degree interactions are not so important to decide the structure. For all cases, lone pairs will always, they will acquire the positions which minimize the 90-degree interactions. Here, such type of symmetry, it gives the C2V point group. Then we will consider dichloroiodate ion, that is the ICl2 minus ion. So it has two bond pairs and three lone pairs. So the three lone pairs here, they occupy the equatorial positions because to minimize the repulsion and avoid the distortion. So and I has 7 electrons plus 2 electrons from 2Cl plus 1 electron from the ionic charge, that is total 10 electrons, which gives us 5 bond pairs, and this is how it gives us a D infinity H point group. So these are some of the other examples that has been shown for predicting the geometry using Vesper theory. Now here some of the bond molecules here in sulfur compounds, it has been shown here. The molecular structure of iodine heptafluoride, the gaseous XCF6 molecule, it was predicted to have a slightly distorted octahedron, but the lone pair, it occupied the less space than the bonding pair. So figure here we can see for XCF6, the best structure is to be distorted octahedron in which the lone pair, it extends outwards through a face that is called as C3b, or through an edge C2b symmetry. Now several conformations of dynamic molecules here it exists. So to actually predict the structure, the different analytical techniques such as Raman spectroscopy, X-ray crystallography, or Raman IR, it has been performed. So then comparing this data, we can predict the geometry which of our XCF6. So it is that XCF6 molecules, it can donate a fluoride ion and form XCF5 plus cation, which is isoelectronic and isostructural with IF5. So this matches also with the predicted theory. So now some of important points that we should remember regarding the Vesper theory. The repulsions are of the order lone pair is greater than lone pair bond pair is greater than bond pair bond pair. So when lone pairs are present, the bond angles are smaller than that which is predicted by rule number 1. So if lone pairs choose the largest side, that is the equatorial in trigonal bipyramidal, if all sides are equal, then the lone pair will be trans to each other. Double bonds, they most occupy more space than the single bonds. And if the central atom is in the third row or below in the periodic table, the lone pair will occupy a stereochemically inactive s orbital, and the bonding will be through p orbitals and near 90-degree bond angles if the substituent electronegativity is less than 2.5. Although this Vesper model has been well received, it is the theoretical basis is still not understood. However, it has some lacuna because it cannot explain various geometries of complex molecules. So it also an improvised or a modern theory has been uh, proposed to counteract this Vesper theory. So then is the Walsh diagram. So here the this method, the Walsh diagram, mostly uses the LCAO, that is the linear combination of atomic orbitals, and MO is the molecular orbitals, that is their combination, so that the geometry of the molecules they may be predicted in a better way. So Walsh diagram is one of the such methods which correlate the changes in energy of molecular orbitals between a reference geometry, that is which has a high symmetry, and a deformed structure that is a lowest symmetry. So let us consider BeH2 here. Here in example, it has been shown in BeH2. So, and we will look at the energies of the bonding, non-bonding and anti-bonding orbitals in it. Now this molecule is bent. So the first 2 sigma g orbital is constructed from the atomic wave functions, that is the symmetric G for Girard, and hence on bending there is an increase in overlap. So the energy of the 2 sigma g orbital it decreases. Then in contrast, the energy of the 1 sigma u orbital it increases on bending. So the wave function it changes its signs. Moreover, here we can also see the p orbital, here it is linear. So here in the bent molecule, here if with the p orbital, linear p orbital in the bent molecule, it overlaps with the hydrogen atoms. Thus the energy of the 1 sigma u orbital it increases. So what happens is the BeH2 has a molecular orbital electronic configuration of 2 sigma g2, 1 sigma u2. Now here the sigma u loses more energy than that sigma g gains. So that is why here the net output is that BeH2 it gains energy. That is why it is linear and it is not bent. So here, although these are the Walsh diagrams, they are associated with certain limitations. It is accurate only for molecules in which there is a large separation between the NS and NP energy levels of the central atom. Now, if the NS and NP separation is small, then the 1U level, sigma U level, it does not rise as rapidly as the sigma G falls, and thus these levels, the exact calculations cannot be made, or the signs, that is the positive sign and negative sign, they cannot be predicted. So here at this session, so here it becomes that although the Vesper model they are not agreeable to each other, these diagrams, Wells diagrams, they certainly give us an idea about the symmetry and the energy and the geometry of the molecules. Some common geometries and their associated hybridizations it has been given here in figure 2.5. Many additional hybridizations are possible for higher coordination numbers which are not known. So here the possible structure may be classified in terms of a coordination number of the central atom and the symmetry of the resulting molecule. If there are two groups about the central atom, it will form angular, that is p2 orbitals, or linear molecules. When three groups, it will form pyramidal or trigonal planar. With four groups, it forms tetrahedral or square planar, and five groups generally forms trigonal bipyramidal. Sometimes square pyramidal is also possible, but when we have six, then it forms octahedral molecule. So stereochemically, active lone pairs additionally lower the symmetry. Also, we should note that the hybridization of the lone pairs will be different from that of the bond pairs. Here, some of the geometries of some common hybrid and non-hybrid arrangements here, it has been shown here. The relationship between hybridization and bond angle is simple for sp hybrids. For two or more equivalent orbitals, the percentage S character here it is given by this relationship, that is cos theta is equal to S by S minus 1 or P minus 1 by P, where S is the percentage S character and P is the percentage of P character. So here for hybridization, sp2, sp3, the atomic orbitals is S plus of the P. So here some of the hybrid atomic orbitals, like for dsp2. So for dsp2, the hybrid orbitals that is involved is dx square minus y square plus 1 s orbital plus 2 p orbital. For dsp3, that is dz square plus 1 s orbital plus 3 p orbitals, that is px plus py plus pz. So this is how the different types of atomic orbitals they are involved in hybridization process. Now suppose in methane, for example, cos theta here, theta is the, that is the angle between the orbitals, between two equivalent orbitals, that is called as the theta. So for methane, cos theta is equal to 109.5 degree. So here in sp3d, the set of hybrid orbitals into subsets of orbitals can be resolved into sp2 and the dp subset. So in water, the bond angle is 104.5 degree. So here cos theta will be given as this, that is 0.250 p minus 1 by p. So which here, putting the values, we can find that p is equal to 80%. So that is the p character is 80% and s character is 20%. So this is how we can calculate the overall p character and s character in methane. So with this, we will this much for today. So in tomorrow's class, we will talk about Bend's rule and the energetics of hybridization. So this much for today. Thank you all.
Thank you, ma'am.
Thank you.
Thank you, ma'am.